time 30t, find q of t and the current function. So since we don't have a inductor here, I use this differential equation, and then I basically substitute the given values, and then I simplified a little bit, and then I got this equation. But we need to find the q of t, we need the complementary function and the particular function. For the complementary function, we need to solve this homogeneous equation. So I rearranged it so that I can like take the integral of both sides simultaneously. And then later on, after integrating it, I got q complementary function is equal to c1 e to the negative 2t. And then for particular equation, since we have 60 cosine here, I assume that particular solution would look something like this. And then I also took its derivative so that I can plug these two into this differential equation. This differential equation, so that I can find missing A and B. And then I did that over here. So this is my work. And then later on, I combined the complementary function that I found and the particular function here to write the q of t. And then we also, and we have c constant here. So I needed to use this given value, which is that at time t equals 0, the charge is 20. So I got the constant. And then since we also asked for the current function, and that for that one, we need to differentiate the q of t. So I did that over here. And then this is the current function that I got.
Great. Anyone has any question? Okay. All right. 素贤
Yes.
Okay. 任君怡、任音频。
Oh, no, not here. Why? I can't. What's the problem? Oh. Let me share. It's okay. Everyone can see it.
Yeah.
Oh, okay. Too small, I guess. Okay. Today I present like a 12.4. These problems we have like an RLC circuit problem. We have L is 2H and R is 120, C is 0 point something, ET is 100, and then we have like a initial I0 is 0, Q0 is 4, and then find the current equation I of t. So first of all, I have the like equation is L I double pi plus R I pi plus 1 over C is I equal E pi t. So we have like a left hand side ET equal 100. So we have the E pi is equal 0. So when the left hand side is 0, so we get a homogeneous like equation. So we have a homogeneous equation. So I like simplify, and then I got the I double pi plus 6 I pi plus 2, 25 I equals 0. So I use like I find like a characteristic like equation, and then I got like a R is, I got like complex, like a root. And then the real part is A equal -3 and B is 4. So the current equation for complex root is equal like a E, like a real part times T, multiplied by C1 times cosine like imagic T plus C2 sine imagic part T. So I plug in A and B into the current equation. I got the equation is E, like power -3 times T multiplied by like a C1 cosine like 4T plus C2 sine 4T. Now I need to find like a C1 and C2 that's missing. So I like a derivative like a current equation I pi equal I get like this equation. I use the products and then some things, and then I find that. So we have like initial I0 is equal 0. I plug in the current equation. I get the C1 is 0, but I still missing like a C2. So we have like a equation, we know it like a L times like I pi plus IR plus like a 1 over Q equal ET. And then we have like a derivative like this is L times like a current initial pi plus like a R like current initial plus 1 over C is Q initial equal like a E initial. We know the E like a initial is like 100, and then I plug in like a LR like a 1 over C. I get like a I like a current initial is like a negative like a 50. So I plug in, and then to here like I like current initial derivatives and then the function, I get like equation like a negative 50 equal 4C2 negative like a 3C1. We know C1 we get like a 0, so I get the C2 is negative 25 over 2. So the current function is like a E power -3 times T multiplied by negative like a 25 over 2 sine 4T. That's the solution.
Nice. Nice. Thank you.
Thank you.
Junyi, 13.3, also power series. Then Yinping, 12.2.
Okay, so it's asking for it to find the power series and also determine the radius of convergence of the power series. So the first thing to do is, one second. So, sorry, one second. Is it the right? Oh yeah, just set it up y of x and y prime of x. And also with the y double prime, this with the summation, which is infinity, that n is equal to 1 for the y prime, for the y of x, and the y prime of x is n equal to 1 times the, just take the derivative. And also with the y double primes is the coefficient is n times the n minus 1, and the x to the n minus 2. Then we set it up, like plug it in back to the equation, y double prime minus y equals to 0. And then, how to say it, like we factor out, or no, like we plug in the numbers that is equal to the 2 c of 2 plus 6 c of 3 times x plus 12 c of 4 times x squared and to the infinity, which is equal to the summation of n to the infinity, that n plus 2 times the n plus 1 times the cn plus 1 x to the n. And then we do, what's that called? Just put that equation back to the y double prime minus y. So we get, and then we can factor out the x of n. Then we get the summation of n equal to 0 to the infinity, that n plus 2 times n plus 1 times cn plus 1 minus cn. Then we can take out the coefficient of x to the n equal to 0, so which is n plus 1 times n plus 2 times c to n plus 2 minus cn equals to 0 for all n greater or equal to 0. Then we do the addition, which is like put the cn to the right hand side and divide by the n plus 2 times n plus 1. Then we can do the next thing, we do the recurrence relation. Just plug in back to numbers at 0, 1, 2, 3, 4, and there's the order, which is the even value, and the odd value, which is n equals to 0, which you got c of 2 equal to c of 0 over 2 times 1. And n equal to 2, which is c of 4 equal to c of 2 over 4 times 3, is also equal, like just plug in back to the c of 2, then we get the c of 0 over 4 to factorial, and then so on. So the general equation for that is c of n equal to c of 0 over n factorial. And for the odd value, which is we plug in the c of 1. C of 1 equal to c of 1 over 3 times 2, which is the equal to c of 1 over 3 factorial. And then the general equation for that is n plus c of 1 over n factorial. So we put it back together, and we factor it out. We could equal to the c of 0 plus c of 1 times x plus c of 0 over 2 factorial times x squared, and so on. Then I just do a separation, like to do the even and odd addition, just to see more clear that's how it's going on, like c of 0 plus, that's the even, c of 0 plus 1 over 2 factorial times c of 0 times x to square. And also for the odd is c of 1 times x and plus 1 over 3 factorial times c of 1 x to the third x cubed, sorry, and so on. So the general solution for that equation, which is equal to the c of 0. So just factor out the c of 0 for the even number. So c of 0 times the summation of n equals to 0 to the infinity is 1 over 2 of n factorial times x to the n. And the odd one is c of 1 times the summation of n equals to 0 to the infinity, 1 over 2n plus 1 factorial x to the 2n plus 1. That's the general solution. And for the, sorry, Professor, what's the p called? What's that called?
I don't know. Radius of convergence.
Yes. The radius of convergence for that solution. So we do the c of C of 0. We take the C of 0 over the C of n plus 1, or C of n and C over C of n plus 1, sorry. So we do the absolute value also. Then we take, just plug in the equation. So 1 over 2 n factorial times the C of 0 over 1 over 2n plus 1 factorial times C of 1. Would take the limit n to the infinity. Then we plug in the infinity value. We get just factor out the 2 of n. So we left 2n plus 1 over C1. Oh, times C of 0 over C1, sorry. And then so the infinity number over any numbers is still infinity. So the series of convergence, oops, sorry, is so the series converge for all x, sorry.
Okay, all right, you tried. Okay, all right, nice. But I will explain because I'm going to talk about this topic. All right, okay, so that's Jun Yi, and thank you. Good try. And Yinping, you're the last one. Anyone else like to present? Okay, I guess the Yinping is the last one, 12.2.
Okay, can you guys see my screen?
Yeah.
And my question is from the homework 12, the question 2. We have ET equals to 60 sine 30t, and we have the equation for ET equals to Li prime plus Ri, and we have L equals to 5, I equals to 20. Then we have 5i prime plus 20i equals to 60 sine 30t. Divide by 5 for both sides. We have I prime plus 4i equals to 12 sine 30t. And first, we need to solve the homogeneous equation. We have I prime plus 4i equals to 0. And that means di over dt equals to negative 4i. Di over I equals to negative 4 dt. And integral both sides, we have ln I equals to negative 4t plus c. And use the e, we can have I equals to e to the negative 4t plus c. We have ic equals to c1 times e to the negative 4t. And for the second step, we need to find IP that the particular solution is the form of IP equals to a times cosine 30t plus b times sine 30t. I prime p equals to negative 30 a sine 30t plus 30b cosine 30t. And substituting in I prime plus 4i equals to 12 sine 30t, we can get negative 30a sine cosine 30t plus 30b cosine 30t plus 4a cosine 30t plus b sine 30t equals to 12 sine 30t. And find the common factor, we have negative 30a plus 4b times sine 30t plus 30b plus 4a times cosine 30t equals to 12 sine 30t. And we can get the negative 30a plus 4b equals 12, and no cosine on the right side, so the 30b plus 4a equals to 0. And we can use the second equation to get b equals to negative 2 over 30a, and plug a into the first equation. We can have a equals to negative 19 over 229. And plugging back, we can have b equals to 12 over 229. Now we can have the equation for the particular solution IP is equal to negative 19 over 229 times cosine 30t plus 12 over 229 times sine 30t, and the initial the general equation IT is equal to IP plus IC, and we have the I0 equals to 0. So plug in when t is equal to 0, we can have negative 19 over 229 plus C1, so equal to 0. So we have C1 equal to 19 over 229. Then final the IT is equal to negative 19 over 229 times cosine 30t plus 12 over 229 sine 30t plus 19 over 229 times e to the negative 4t. That's it.
All right. All right. Okay. Anyone else like to present today? Okay. If not, it's my turn. So we're going to talk about power series as a solution of the differential equations. So let's review some elementary power series concepts. Remember a power series, right? A power series, because in the future, right, when we really talk about a solution for applications, it turns out to be finite terms, right? We're treating the tails, we're talking about k terms. We're going to take about k terms, then the k plus 1 until the infinity. We just assume them tend to 0, when we talk about real applications. But for now, we're going to use power series as a solution, which is the infinite. You could think as a polynomial with infinite many terms. So it has this form, right? A constant, which is a 0 degree, x raised by 0, linear, quadratic, so on and so forth, right? So after here, that's n degree, then it keeps going on to infinity because we let n, so the index we start from 0 and goes to infinity, so we have infinite many terms we call power series. But this is a solution about 0 because x minus 0 is just x, so x raised by n. But normally, x around 8, right? So x minus 8. So I have this x minus 8. We have those famous ones, right? Those famous guys. We need somehow not to memorize them, but to get familiar with them. Once we see a pattern like this, we know there's e to the x. And this x can be any expression. This x could be 3x, could be x squared, could be something else. X is just in general, right? This x is a placeholder. But we have this kind of form. We start with a 1, then x over 1 factorial, x squared with a 2 over 2 factorial, so on and so forth. But again, this x can be any expression. I also have famous cosine x as the infinite series. What is that? That's 1 minus x squared over 2 factorial plus x raised by 4 divided by 4 factorial, so on and so forth. So we have these alternates, the sign alternates, positive, negative, positive, negative. So we have this alternate series. So this is the nth term, right? So nth term, a general term in the series. So this one is so that's a general term in the series for e to the x. This is a general term, nth term, in the infinite series for cosine x. Right? So x raised by 2n divided by 2n parentheses factorial. Okay, sine x. Sine x, we have something very similar. The nth term is -1. We also have alternate series. We have x raised by odd number, 2n plus 1 over 2n plus 1 factorial. Then we have a rational one, rational expression, 1 over 1 minus x. This is 1 plus x squared, da, 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 da. The nth term is x raised by n. We have 1 plus x, right? 1 plus x. This one alternates. Again, we get an alternate series. 1 minus x plus x squared minus x cubed. So the nth term is -1 raised by n, x raised by n. So this is from our calculus 2 courses, right? Just a review. If anyone has any question, feel free to stop me at any time. Now let's see e to the 2x. Right? Again, you know, this x here, just a placeholder. It can be any mathematical expression. Right? So this gives the example saying, okay, now x is e to the 2x. So what do? We just change this x to be 2x in the formula, right? So 2x raised by n. And that becomes 1 plus 2x plus 2x squared over 2 factorial plus 2x cubed over 3 factorial, right? So on and so forth. Cosine 3x. Now in the infinite series, x now is 3x. So we just change the spot of x to be 3x. What's important is the pattern of the terms in the infinite series. Right? So the x here, just a placeholder, can be any mathematical expression. Okay, definition. If the Taylor series of f of x converges to f of x for some open interval containing x equals to 8, we see f is analytic at x equals 8. Right? So just a definition. Just definition. Let's see this example. This example is saying, okay, f of x equals to e to the x is analytic everywhere. So what does that mean, analytic? Which means it converges, right? It converges, the Taylor series of f of x converges to f of x for an interval containing such 8. Then we see f is analytic at that.
I have a question, Professor.
Yes, Gregory, go ahead.
Sure. What does it mean f of x converges to f of x? Like, is that what we expected? Or
okay, let's go back to calculus 2. Remember calculus 2 talk about convergence?
Yeah.
Right. Convergence. Okay, we have series, we have 2 types, right? Either converges or diverges. Right? If it converges to something. So this case is saying converges at f of 8, basically.
Okay.
Does it make
Got it.
Okay. If it diverges, there's nowhere to be found. If it converges, it has to converge to something. But this is not obvious to see, but you could think, you know, around is such a, it converges for f of 8.
Got
So
it. Thank you so much.
You're welcome. You're welcome. E to the x is analytic everywhere. And 1 over 1 minus x is analytic everywhere when x equals 1. All polynomials and rational functions whose denominator are not 0, right? Because rational functions denominator cannot be 0 are analytic. Okay, let's see power series operations. So let's see, f of x can be represented as a power series. And the g of x also can be represented by a power series, but with different coefficients. Then we can add two functions or subtract two functions. That will be the sum or subtraction or addition of the two power series. And if we multiply the two functions, that will be multiplying the two power series also. So give another power series with the coefficient Cn. So usually we want to know for what values of that series converges, which is back to calculus 2. Let's try this theorem, radius of convergence, calculus 2 course. So we have this power series, right? I suppose this rho, we call rho radius of convergence. We don't really need this rho, but just for convenience. Okay, for convenience. Instead of talking about every time talk about the limit of n goes to infinity, absolute value of Cn over Cn plus 1, right? You could just see rho, the radius of convergence. Okay, this rho exists, but if the limit exists, right? So either suppose this rho is this, exists, or is infinite. So we have this A, B, C, 3 bullet points. If rho equals 0, then the series diverges for all x not equal to 0. So 3 situations. Okay. If the limit tends to be 0, then the series diverges for x not equal to 0. If the radius of convergence is greater than 0, positive number, but less than infinity, which means is a finite number, then the series converges if the absolute value of x less than rho. Right? This is all from calculus 2. And diverges if it's greater than rho. If it equals rho, we have to check the convergence some other way. If rho equals to the infinity, which we already see 2 examples, and she showed 1 example, and Junyi showed 1 example, right? If the limit equals to infinity, then the series converges for all real numbers. Let's see these some examples to review. We want to find the radius of convergence for this following. So 1 over x, that's this series, e to the x, this series. This one Cn equals 1, Cn plus 1 equals 1. And rho, limit of the ratio, remember this is a ratio test, right? Which is 1. So for all x, absolute value of x is less than 1, then the limit of convergence goes from -1 to 1, right? The same. So these two are the same expression. Absolute value of x less than 1, that means x is in between -1 and 1. So the infinite series converges. For example, if x equals to 2/3, which is less than 1, then remember the ratio, that's 1 over 1 minus x, or x equals to 2 over 3. 1 minus 2 over 3, that's 1/3, 1 over 1/3, which is 3. So it converges. It's a finite number. But if x is greater than 1, if x is 3/2, it diverges. Right. Let's see this one. Cn equals 1/n factorial. Cn plus 1 equals 1/n plus 1 factorial. We're trying to find the radius of convergence. The nth term divided by the n plus 1th term. So that's 1/n factorial divided by 1/n plus 1 factorial. That becomes n plus 1 factorial divided by n factorial, which is just n plus 1. Well, as n goes to infinity, so n plus 1 goes to infinity. So the radius convergence is infinity, which means it converges for all real numbers. So this just give an example. Let's see this example. We have this 2 raised by n divided by n squared. With power series with Cn is this term, 2 raised by n divided by n squared. Oh, so the nth term is 2 raised by n divided by n squared. The n plus 1th term is 2 raised by n plus 1 divided by n plus 1 squared. We'll try to simplify. 2 to the n plus 1, so get a half. N plus 1 squared, n squared, we can write together as n plus 1 divided by n squared. As n goes to infinity, we see this one becomes 1. N plus 1 over n becomes 1. So we just get half. So it's a finite number. So the radius of convergence is a finite number. Then we see the radius of convergence is a half. Right. Power series converges if absolute value of x less than half, or x is in between -half and half. If anyone has any question, feel free to stop me anytime. Okay, let's see this theorem. Okay, so this is a power series, right? And we write as a function. We write this function as a power series. Converges on an open interval I. Let's call it open interval I. Then f is differentiable on I, and the derivative is just power. Remember the power rule, right? Take down n, multiply n with Cn, then subtract 1 from n. So get this, n times Cn, x raised by n minus 1. Power rule. Because, this is just like infinite many terms of polynomials. Let's see this example. F of x equals 1 over 1 minus x. We know this converges when the absolute value of x less than 1, or when x is in between -1 and 1. So the power series is just in this 1 plus x squared, right? General term, just x raised by n. When we take a derivative, we just take a derivative of each term. Derivative of 1 is 0. Derivative of x is 1. Derivative of x squared is 2x. Derivative of x cubed is 3x squared, so on and so forth. So the nth term derivative, x raised by n power rule, is n times x raised by n minus 1. Theorem. So one power series, if one power series with coefficient an equals to another power series with coefficient bn for every point of x in some open interval, then the coefficients has to agree term by term. An equals bn for all n. So some differential equations can be solved by assuming the solution to be a power series. then its derivative will be just this by power rule. So we can use that to plug in back into the differential equation. Let's see this example. We have y prime plus 3y equals 0, right? And we see the example of y prime minus 3y equals 0. So first step, we just let a solution y to be a power series. Then the y prime by power rule, we get this, still a power series. But look at this index. This index is starting from 1 now, because the constant term becomes 0. So substitute y prime and substitute this y and y prime into the differential equation. So what do we get? We get this, right? This is our y prime. This is 3 times y equals 0. So in this case, we can line up the coefficients, okay? Because this one, we can think that's just C1, 1 times C1, 2 times C2x, 3 times C3x squared, so on and so forth. The nth term will be n times Cn x raised by n minus 1, okay, the nth term. And then this one can be written, so we can re-index, because this starts from 1. We can re-index. We want the n start from 0. Okay? We want the n start from 0. So basically means we want to reduce. So this n start from 1, this n start from 0. So n now was 1 before. Now because n start from 0, so this term becomes n plus 1. Right? N becomes n plus 1, and n minus 1 becomes n. Because in this case, we have n's 1, starting 1, 1 minus 1, 0. But here, we're starting from 0, so this is x raised by n. So we re-index this, right? Re-index the differentials, y prime. So we rewrite like this one. Because if we combine two summations, the index has to equal to each other. The index has to be consistent. In this case, we cannot do any combination because this index starting from 1, this index starting from 0. So we just have to re-index the differential one, the y prime. So we re-index, get this. Now we can add some terms. So we have this one, y prime. We have this one, y. Right? Now we can factor xn. Right? So the coefficients we have this. We have n plus 1, cn plus 1 plus c, 3n. And this equals to 0. That means the coefficient has to be 0. Think about it. You have these infinite many terms. How do they become 0? They become 0. It's not x to be 0, but these coefficients adds up to be 0. Actually, every coefficient has to be 1, has to be 0, not adds up to be 0, because we have different terms. We have x raised by n, x raised by n minus 1, so they're not like terms. Right? So for an infinite power series to be 0, all the coefficients has to be 0. So we can say, okay, we can take the nth term. So typically nth term to be 0. Right? So from here, we can find the relationship of those nth term and n plus 1 terms. So in this case, we see the n plus 1 term equals to the previous term times -3 over n plus 1. right? It's better to write a negative 3 over n plus 1 Cn. So we see clearly the relationship between current term and the previous term, or the term and the next term. Obviously, this is recurrent relation. Right? It's just, talking about terms. Cn represents any term, n plus 1 representing the next term. So if we know, n term, we know n plus 1 term just by calculation. So let's see some examples. If n is 0, well, we have negative 3 over 1 Cn. And C1, right, so n equals 0, that's C1's term, equals to negative 3 C naught. So the first term. Same thing, if n equals 1, the second term, to the calculation, is 9 over 2, is negative 3 over 2 of the previous term, but 3 squared over 2, or 9 over 2 of the first term. Right, we can keep going. So we see this is a recurrent relationship. So every term can be represented in terms of the first term. So you will see, we find a pattern of this. We have negative 3, negative 3 squared, negative 3 cubed, negative 3 raised by 4. So we see negative 3 raised by n. In the denominator, we see 1, 2, 2 to the 3, 3 times 2, factorial, right? 2 times 3, 3 factorial. 2 is 2 factorial. 1 is 1 factorial. So C4, 4 factorial. Cn, so this n factorial for the denominator. So a general term is Cn equals negative 3 raised by n. You can split this to tell this is an alternating series. But you can write negative 1 and 3 together, right? Raised by n, divided by n factorial of the first term. So a typical solution would be, a general solution would be y of x. You can substitute in. Then the nth term is this one. The nth term is this one. Substitute in the series. So negative 3x, because then we have this x raised by n here. Get negative 3x raised by n divided by n factorial. Right. Obviously, oh, I'm sorry. I missed, oh, right, x is here. And obviously, we see this is x raised by n divided by n factorial. But in this case, x is negative 3x. So that's e to the negative 3x. So typical solution for the differential equation is this. E to the negative 3x multiplied by some coefficient. Anyone has any question? Gregory, yes. Oh, all right. Do you have any question? So I don't know when will you cut off. Should I repeat the example? Suxian, yes, question?
Could you repeat for the line up coefficient of the C power x, because I don't know why you said like n equal 1 and n equals 0. I just heard you said like n equals 0. You cannot do that, so you choose like n equal 1, and then become like n equals 0, the power
Okay,
series.
Yeah, so we want to combine two power series, right? You see this one? This is one power series. This is another power series. If we combine those two, the index has to be consistent. The index has to agree with each other. But this one starts with a 1. This one starts with a 0. Right? So we need to do some reindex. So we want to reindex this first one. We want to reindex this one starting from 0 also. So how do we do that? You could think, if this is a difficult thing, you think this way. You think let k equals to n minus 1. I'm typing in the chat. Because the index, you can use any number. Instead of using n, think about the n, you think of as a k. So k equals n minus 1. Then you see, then this one I highlighted, you can start with k equals 0 up to infinity. Then inside, so the n now, so if k equals n minus 1, what's n? N equals to k
1.
plus 1.
Oh yeah, k
right?
plus,
So then you have to change the n inside the summation, has to be k plus 1. Then cn to be ck plus 1. Then x raised by n minus 1, it becomes x raised by k. Right? Then you just change k back to n.
Okay.
Does it make sense? This is called reindex.
Okay.
Does it make sense?
Yeah, that makes sense. Yeah.
Okay. Gregory, you have a question? Gregory was, right, he was his audio cut off. Is he here? I think he's gone. But the good thing is you can always rewatch because the class is recorded. Okay, anyone else has any question? All right, so that's one example. Let's see this example. So we want to solve this equation. We have x plus 2 y prime plus 2y equals 0. And we're given an initial condition. That means we want to find a unique solution, a particular solution, a unique solution for this initial condition. Also, we want to find the radius of convergence of the solution. We started with the power series, right? And then its derivative is this, right? Derivative n starts with from 1 because the first term, the constant term, becomes 0. And then we substitute back into this differential equation. So we get x plus 2 times our new y prime plus 2 times y equals 0. Then, so this is x plus 2. So we change 1 to be x times this summation, this series. Right? So x raised by n minus 1 times x, that becomes x raised by n. Then we have this 2 times this series. This 2 we can put it inside, so that becomes 2n, right? So this is 2 times n, so that becomes 2n. And this term also 2 outside, you know, can put a 2 inside, 2cn. Again, we want to reindex those two because we want to combine them. Right? We want to combine them because they are all, you know, power series. We want to combine them. So we need a reindex. Again, if you think n is difficult, you just think k. You let k be n minus 1. Right? Then n equals k plus 1. Right? So k start from 0. Then n equals k plus 1. N minus 1 equals k. So this one can be rewrite as k goes from 0 up to infinity. 2 times k plus 1. Then ck plus 1 and x raised by k. Well, a variable is a variable. Once you use k to reindex it, change back to n, right? Because it's just a dummy variable to hold the place. So this process is called reindex. So we get this. Similarly, we want to reindex. Okay, we did this one. We did this to n, right? Similarly, we're gonna do something similar to this one. We let n basically equals to n minus 1, right? Or k equals n minus 1 if you have to use another variable. Oh, hold on a second. So, okay, we don't really have to do that right now. So we want to combine those two. We want to combine. So this one is changed now. We want to combine. See, this is x raised by n. This is x raised by n. You see why we don't want to reindex this one now? Because if we reindex, right, we get an x raised by n. So think about k equals n minus 1, right? K equals n minus 1. So the power wouldn't be same as this, so it wouldn't be able to combine with those two. So now the nth term are lined up, and the index are consistent, so we can combine those two power series. Combine those two power series, what do we get? We get 2n, get this 2cn, we get this 2n plus 1, 2n plus 1. No, okay, let me see. I made this, okay, it's typo or I made a mistake. Because I didn't reindex this. Right? I didn't reindex this. If I don't reindex this, how can I combine those three? Sorry, that's a mistake. I should have reindex this. If I reindex this, I let n be n minus 1. Or think as n, k equals n minus 1. All right, then n would be k plus 1. Okay, so this would be n plus 1, cn plus 1. This would be n plus 1. So this one should have one x term. Anyway, let me see. This answer should be off. Two n plus 2, 2n plus 1. Okay, so you see the answer I didn't include in this. Oh, yes, I did. So that's n plus 2. N plus 2. Okay, sorry guys, that's a mistake here. That's a mistake here. This one needs to be reindexed, and this one has x term in it. All right, this one has x term in it. And the answer should be just cutting from this. How do I fix this? I just take this part. Okay. Just take this part. Then all the answers is not exactly right. All the answers are a little bit off. But let's just go over the steps. All right. So the steps is very similar as the previous one. We want to find out the relationship between the current term and the next term. Once we find out, right, we want to find the pattern. So we have this pattern. Once we find out, we calculate a couple of them. Here we calculate 4 terms, right? Then we find the pattern. We want to find out the pattern of this. So then what do we see? We see the denominator. We have 2 times 2, 2 squared, 2 to the 3rd power, 2 to the 4th power, so on and so forth. And the numerator we have 3, -4, 5. We see alternates, right? The term is an alternating series. So what that means, we have -1 raised by n. Then we see this term, the first term is just 1 over 1, or 2 over 2. It's just 2 over 2, 2 over 2. Right, so the position, so C1 is 1 plus 1, right? 1 plus 1. And so we form a general term, which is an alternating series. The numerator is the position plus 1, where n shows the position, plus 1. And the denominator is just 2 raised by 1, 2 raised by the position. 2 raised by 1, 2 raised by 2, 2 raised by 3, 2 raised by 4. So we find the pattern, we observe the patterns, then we form a general term. So this is recurrent. So the nth term is with this coefficient of the first term. Anyone has any question? Then we plug back in the Cn. Right? So Cn, we get this. If we're given initial condition, in this case, we are given initial condition. Yes, we are given an initial condition, so we can get a unique solution. So get a general term of Cn, we plug back in to our solution. Now we just have to find out this constant. We're given an initial condition y of 0 equals 3. So we plug in, right? We plug in, just get this. Then, so, all the terms with x is 0. So x raised by x is 0. Oops. We have this n plus 1 here. It's just the first one survived. Right? Because 2 to the 0 is 1. -1 to the 0 is 1. 0 plus 1 is 1. X to the 0 is 1. So everything is 1. To get a C naught, the first term is 3. So we get a unique solution for the given initial values. Anyone has any question? I'm sorry for the typo, for the mistake. Now find the radius of convergence. Again, we take the ratio of the 2 consecutive terms, right? So the nth term represented this way, n plus 1's term, represented this way. We do a little bit of calculation. 2 raised by n plus 1 divided by 2n's, that's just 2. Right. Then n plus 1 divided by n plus 2 will limit when n goes to infinity, that becomes 1. So just 2. Again, similar to previous one. So rho equals to a finite number. Equals to a finite number that tells us the series of convergence, the radius of a convergence is 2. Right? So which means the series converges when x value is in between -2 and 2. Okay, let's see this example. I hope I did not make a mistake on this. We have x squared y prime equals to y plus 1 minus x. So we want to find the radius of convergence. We want to find a solution, right? Then also radius convergence for the solution. We do the same thing. We say, okay, let the solution be a power series. Then derivative is this. Then plug back into these differential equations. We get x squared times y prime equals to 1 minus x plus y. Then this x squared we can combine with this x raised by n minus 1. So that becomes x raised by n plus 1. Then this one we have 1 minus x So what do we do? So this starting from n equals 0, right? Let's see if we reindex this. We reindex from, let's calculate n equals 0. When n equals 0, we have c naught x raised by 0, which is 1. So we get this constant, right? Constant plus this 1. When n equals to 1, we have c1 x raised by 1. Then right, we have c1, so c1 x raised by 1, our second term. But remember, we have this 1 minus x. Then, so the reindex this, no, the rest of the 2, not reindex. So basically, we calculate the 2 terms from here, when n equals 0, when n equals 1. Now, we're left with the rest of the terms starting from n equals 2 up to infinity. Any questions? That's just, calculating 2 terms from here, plus those 2 terms, so we get this. Again, we want to line up, or we want to reindex this. So the n start from 1. Sometimes if we don't really understand the summation sign, we can read out some terms to help us to understand, right? And then we can reindex from n equals 2, because we want to combine with this guy, because this starts with 2, n equals 2. So if n equals 1, we just get c1 x squared, right? So n is 1, and c1 x raised by 1 plus 1, so c1 x squared. Then we just have to write the rest of it in summation sign. That means n starts from 2. Well, n starts from 2, we get 2, n start from 2, starting from this one. X raised by 3. Oh, this is n start with 3. This is n start from 3. Okay, that's a mistake here too. So this shouldn't be n minus 1. This should be just n. right? You see this one. So if I rewrite C1x squared, oh, hold on a second. Okay, I still need this one. Okay, so this one equals to this, right? How am I going to, now I need to reindex. So C1, that's why if I start with 2, n equals 2, I have to do 2 minus 1. 2 minus 1, right? 2 minus 1 to get a 1. Then C, 2 minus 1, which is C1. Then x squared. So when I reindex, so I reindex this to be this. To be this. Then this equals to this, right? Then this equals this. So I can match up the coefficients. So when I match up, I get a C naught plus 1 equals 0, because there's no constant term, because this is stuff from x squared. And the C1 minus x also equals 0, because this series x variable start with square, x start with 2, x squared with this. So this one equals to this one. But this one is 0, this one is 0, so that's why I get a C naught equals -1, C1 equals 1. And then this Cn equals to n minus 1, Cn minus 1. Cn equals n minus 1, Cn minus 1. So if I calculate a couple of terms, so C2 will be 2 minus 1, C2 minus 1, which is C1. So I get C2 equals 1, because C1 equals 1. So I get C2 equals 1. Then C3, I do the same thing, 3 minus 1, which is 2. C3 minus 1, which is C2. Well, what is C2? C2 is 1. So I get a 2 times 1. Or C4. C4 is 4 minus 1, which is 3. C3 minus 1. C4 minus 1, which is C3. Well, what's C3? C3 is 2 times 1. So I get 3 times 2 times 1. You see factorial, right? So that means Cn equals n minus 1 factorial. For n greater than or equal to 2, because it won't work for C naught. C naught is a special case equals -1. So when we do the recurrence of series, we can forget about the finite terms. So this C0 does not work for this one. So we just forget about it. We're going to forget about a couple of finite terms. How do we forget about it? We limit n. We say, okay, for n greater than or equal to 2 in this case. So we forget about this C naught, we forget about C1. We want the n to start with C2. We want the n to start with 2. So we're able to get this. So Cn equals n minus 1 factorial. So plug back in Cn into the solution, y of x. Get this -1 plus x. Moises. Oh, sure. Sure, you can always watch the recordings. All right. Then we check the convergence. Once we have a solution, right? We have this solution. We check the convergence. We take the limit of the ratio, a current term and the next term, the current term and next term, n minus 1's term, n's term, and n plus 1's term. That's just 1 over n. When n approaches infinity, 1 over n approaches to 0. So the series, remember when rho equals 0, that's the A, bullet points of A. See, the series diverges for all x not equal to 0, which means the series only converges when x equals 0. Any questions? Okay, let's see this example. So we have double prime. We're given two conditions, initial conditions. We want to get a unique particular solution. Again, we say, okay, y is this power series, y prime has this form, and y double prime will keep applying power rule, right? We get n times n minus 1, but now x raised by n minus 2, right? Then we plug back in. We plug back in to the differential equation to line up or reindex. Okay. So this is n starts from 2. We want n start from 0. So basically, we let n equals the k plus 2. Then back up to, change k back to n. So then this n becomes n plus 2. N minus 1 becomes n plus 1. So we have this. So Cn becomes Cn plus 2. X raised by n plus minus 2 becomes x raised by n. So we reindexed. Now we can combine those two power series because the index are consistent now. And we get a coefficient of x raised by n is this one plus this one. Right? Both are coefficients of x raised by n, and the summation index are consistent. So we can combine the coefficients of x raised by n. Well, when the whole series is 0, that means all the coefficient is 0. So the coefficient is 0. Then we try to solve for the relationship between, we have n plus 2 term and n's term. So n plus 2 term equals to negative Cn divided by n plus 2, n plus 1. To get a relationship, so this is a general relationship in terms of n's term and n plus 2 term. So we can apply n equals 0, 2, 4, 6. Right? Because we see Cn plus 2, skip the C1, Cn plus 1. So we want n to be those even numbers. So we'll calculate. N equals 0, get a negative C0, right? Divided by 2 times 1. N equals 2, plug back in, we get negative 1 squared C0, 4 times 3 times 2 times 1, factorial, right? 2 factorial, 4 factorial, then for n equals 4, 6 factorial. Right. Then we see the pattern. 2 times 1. Right, so this factorial. 4 times 3 times 2 times 1 is this factorial. So on and so forth, that's this factorial. So it's the position being factorial. So this is C2n, so it's 2n factorial. And the series alternates, right? So negative 1 raised by n. Anyone has any question? Now, okay, so that's for n to be even numbers. What if n is odd numbers? Let's try n equals some odd numbers. Then C3, we will get this. C5, we will get this. C7, we get this, right? So we get another series, general form for the odd terms. For the odd terms, we get this C2n plus 1, negative 1 to the nth power divided by 2n plus 1 factorial of C1. So for even terms, I have this. For odd term, we have this. So plug back in, right? Calculate a couple of terms. We get y of x equals to c naught, you know. Calculate a couple of terms, we get this pattern. For even, for odd, we get this pattern. You know, obviously, this is cosine, this is sine. So our solution is C naught cosine x and C1 sine x. And if we take derivative of this, cosine is negative sine, so get the negative C0 sine. Derivative of sine is cosine, so first derivative of this. Then we use our initial conditions. So y of 0 is 4. Y of 0 is 4, so x is 0. This all becomes 0. X is 0, this all becomes 0. We're only left with 1 times C naught. So that means C naught equals to 4. Then use this second condition, y prime. Y prime of 0 equals to 6. Well, sine 0 is 0, cosine 0 is 1. So C1 times 1 is just C1. C1 equals 6. So get C1 equals 6. Plug back in. C naught is 4. C1 is 6. So get this unique solution for the two given initial conditions. Anyone has any question?
Do we need, for the final exam, do we need to memorize the Taylor series?
You don't need to memorize it. You need to be able to detect which pattern is that.
Okay.
You need to get familiar with it.
Okay, so like I need to know e to the x is x to the n over n factorial. And
right.
Okay.
Right. So at least the 5 of them. Right. You need to get familiar with that 5.
Okay. Thank you.
Okay.
Professor, I have a question as well.
Yes.
Will you be making the final exam or the math department's going to be making it?
I think I'm making it.
Okay, I got it. Thank you.
You're welcome. Okay, that's all I have to say for today. Anyone has any questions? Gregory, you're back.
Yeah, I have a question. I think it was very much earlier in the slide.
Okay. Yeah.
Let me check. I think it was page 6.
Page 6.
Uh-huh.
Okay, here.
Yes, you see where you have the denominators on like the right-hand side of the page? A little bit down where you calculated values for n.
Okay.
Uh-huh. You said the denominator was n factorial?
Uh-huh.
Or was because I was a bit confused on that one.
Oh, okay. You observe the pattern. because we need to form the nth general term. So we need to observe the pattern. Hold on a second. Okay. So we see the first one is just 1, right? 1 is just 1 factorial, right? But this one won't be able to tell. So we observe, we see, okay, C1, the denominator is 1, and C2, denominator is 2, and C3, we get 3 times 2, and then if we do C4, because that comes from C3, right? We get 4 times 3 times 2.
Okay.
So this 2 actually is 2 times 1. We'll just ignore this 1.
Yeah.
Because C1, C naught has this 1 as a denominator. So this is 2 times 1. So this is 3 times 2 times 1. This is 4 times 3 times 2 times 1. That tells you that's n factorial.
Okay. I think it was just the fact that the you can ignore the ones. That's what made me a bit confused. But I got it now.
Oh, okay, great.
Okay. Thank you, Professor.
You're welcome. You're welcome. Okay. Anybody else has any question? Okay, Ron. All right. Thank you. Have a good weekend. Hope more people to present the next class. Okay, let me stop recording.